So I have this sort of act going with Paul now where he speaks and then I speak more about what he was doing. And I was in his talk this morning. I realized watching his talk what talk I should give this evening, so I went back to my room and changed all my slides around. And we're going to do Vegas next week. We're going on the road. I've never seen him look so worried before. Well, anyway, so here we are. So I want to talk to you about something which is essentially an extension of the measurement techniques that were being discussed this morning, where you were trying to measure properties of attosecond pulses. And that basically involved making electron wave packets with attosecond pulses, and then using IR pulses to mess with those wave packets, as it were. And so this, I want to talk about something that's similar, but here you take the attosecond pulse as a given, and you mix it with an IR pulse, and you see if you can learn something about the strong field physics that, that the IR pulses do. So in these talks, the attosecond pulses are actually a tool for doing strong field physics, is the idea at least. And I have many examples of that, and I'll just stop it. So it's the same people still working and helping and being wonderful. Oh, wait. All right, we can come back to that. So as you saw from Paul's talk and anything else, that strong field physics has made a lot of contributions to attoscience. It really makes it go. The generation of attosecond pulses, the metrology for attosecond pulses. Attosecond science was essentially a metrology problem for at least 5 years, I would say. It was clear that attosecond pulses were being made. It's just the shortest pulses ever made, and so how do you measure the shortest thing? Because your usual measurement techniques for measuring something is go get something shorter, smaller, right? And measure it. So you don't have that. So big contributions to metrology and a lot of applications. And one of those applications is to strong field physics. And that's where you combine the attosecond pulse with a strong infrared field to do things that you cannot do with the infrared field alone. Now, to what extent do you want to really do this? And is this the sort of, it's a little intimidating after following Margaret, because I have like no applications really. I mean, this just interests me a lot and has for a long time. So, and we've managed to get some experimentalists interested from time to time in doing some of this. So you'll see that as we go. But I think it's very interesting. So, and I also took all the equations out of the talk as well. So I'll do equations on Friday morning, I promise. I have equations, but I took them all out. So here's basically the idea, is that if you make an XUV pulse, then you can also combine it with an IR pulse with some delay between them. And you can see what happens in your system as a function of the delay between these two pulses. And I just want to sort of make a point here that many students might not be aware of. As we talked about yesterday, the spectrum of these two pulses is completely separated, right? I mean, this is 1 EV light, this is 20 to 100 to 1,000 EV light. These spectra have no overlap between them. So there's a lot of, right, often when people do transient absorption with pump and probe pulses, they are basically derived from the same spectrum. So one of those pulses will be a piece of the spectrum of the other. So there's all sorts of complications that come with that you don't have in this case. There's one other really cool thing about this, which is this is sort of the typical view of sort of pump probe or two-color spectroscopy, where you have two envelopes and they're separated by a delay, where the delay talks about the separation between the peak of the two intensity envelopes. But here, you can of course do much, much better because, and this is sort of an idealized version of what one of these experiments would look like. And it's worth going through it just to see what I mean. But the point here is that the synchronization between the XUV field and the IR field is at the sub-cycle level. In other words, this tau is between the peak of the attosecond envelope and one of the teeth in the pulse, this is the intensity envelope of the IR pulse, right? So this is just the field squared. And this delay can be extremely precise. It can be the delay between the peak of the XUV field and one of these teeth, or halfway between, right? So you have this incredible synchronization. The reason you have that synchronization is because the IR pulse that you're going to use in this experiment is a replica of the pulse that made this XUV pulse. So, and that's sort of what's happening down here. An IR pulse comes into a beam splitter, it gets split into two pieces. One piece goes off to do high harmonic generation and makes some sort of XUV attosecond pulse. It's put through some sort of a delay line. So it acts as a pump. And then the rest of the IR pulse comes along and it acts as a probe and in some sample here. So you can see in some sample what happens as a function of this delay with subcycle precision. Now and so it's, I hope that's kind of obvious that this kind of works, at least in principle, and it works in practice as well. So this is the application, so I just want to go through sort of some of the things that you can do with this. Some of the things that we've done over the years is look at electron wave packet interferometry, so we have two attosecond wave packets and interfere them in collaboration with the Loon group, also with the Loon group, attosecond control of ionization. We'll talk about that a little bit. An attosecond quantum stroboscope. And the one that I want to start with is strong field quantum path control using attosecond pulse trains. Because we talked the other day, and I think I said maybe one too many times, that at the level of the time-dependent Schrodinger equation of the single atom interaction with the field, it's very hard to separate out the different contributions to any given radiation process. And that was, what's the word I'm looking for? Not true, as it turns out, right? Because the proviso there was that if you couldn't control the ionization in any way, then you couldn't select among the various ways in which the radiation could be made. But we stipulated that the radiation that we were looking at, the attosecond radiation, was an ionization-driven process. So if I can actually control the ionization process, then I can control the light emission as well. All right? Now I want to stipulate again, this is not like an optimization scheme. I'm not doing this to make a better attosecond source or any of that sort of stuff. It's because I want to study dynamics this way, strong field dynamics this way. So here were the equations that we had last time. Tonight I'm basically just talking about the time-dependent Schrodinger equation. So we're just talking about the results of calculations where we start with a wave function. For a lot of the evening I'll talk about helium. I'll talk about relatively low frequency light that is below all of the doubly excited states in helium. So we can think of this as essentially a system where one electron gets excited. So I have a pseudopotential here that describes that, just derived from the Hartree-Fock potential for the ground state. And I have some electric field here, which is going to be a combination of IR and XUV fields. And so then I'm going to calculate the time-dependent wave function on a grid numerically, and I'm going to use that to calculate things. So what the things are as we go along. So this, I want to talk about this seeding and control of high harmonic generation with an attosecond pulse train. So to start with that. And these were some LSU people that worked on it over the years, and there was collaboration with two different experimental groups. Mark Rocking, when he was in Amsterdam, he's now going to Berlin. This was sort of, I think this was the very last experiment they did in Amsterdam, and then Ursula Keller's group in Zurich. So here's the idea. The idea is just what I've already said. The red curve here is the infrared laser cycle. And I'm going to have an attosecond pulse train made from combining some number of high harmonics. Usually it's going to be like the 17th to the 21st. So they're going to be centered around 25 electron volts. So right around the ionization threshold in helium. And so each of these pulses in the attosecond pulse train, they are de facto separated by half a cycle, about 1.3 femtoseconds. And each one of these can cause a little burst of ionization or excitation. And the delay, as I said, is controllable. So it could happen at one delay or another, and we can look at what we get as a function of the delay between these two fields. And so what I think of this as doing is sort of injecting electrons into the strong field with the attosecond pulse. So here's the idea for the quantum path control. The idea is by controlling the time of ionization, we can choose one of several what would otherwise be interfering contributions to the strong field process, especially in this case, hyperharmonic generation. And in general, we can hope to better understand, perhaps control the strong field process via this method. So, another slide, let's say. Let me go past this. But the idea here is that you have one gas, again, I think it was xenon in the experiment that Mark Rocking did, where they produce high harmonics, and they select some number of them to make an attosecond pulse train, and then they do the experiment in helium, combining an infrared pulse and an IR and the XUV pulse. So why do this? Or at least what's an interesting contrast? We've talked a lot about tunneling the first couple of days, right? And so here's what happens, right? We saw in Lars's wonderful talk last night all about how these wave packets get formed. We've seen two very good movies. Your movie had so much better colors than mine. No, you didn't see my movie, but yeah, well, I know my movie. Yours looked so much better. I need your people. But anyway, here's the point. All these tunneling wave packets are essentially identical, right? I mean, that was really Lars's point. You don't, by choosing a different system, you can't make a tunneling wave packet that's all that different. Or it's hard, let me put it that way. They're always born near the peak of the IR cycle. The duration of these wave packets is strictly controlled by the IR intensity. The higher you raise the intensity, the smaller is the tunnel, the shorter, the longer the time over which it can come out. It's born outside the potential well, essentially with an initial velocity of 0. It's very hard to change those parameters. And the ionization step is highly nonlinear, right? Which is cool in some sense because it means that when you do an experiment, you're seeing only the result of essentially the highest intensity in your focal volume. But what if you're interested in looking at how things vary over a very large range of IR intensities? It's hard to look at that by tunneling. You can't do a low IR experiment. So the idea here is, how about if we use an attosecond pulse train to drive the ionization? Now, because the IR ionization process is so nonlinear, by turning down the IR intensity just a little bit, we can essentially choke off the infrared pulse contribution to the ionization. We can't turn it off completely, but we can turn it down almost at will, because if you have a little bit too much, you turn your intensity down 5%, it goes down, right? I mean, as Lars showed you, it's an exponential. So let's say you use the attosecond pulse to drive the ionization, and the IR pulse is just there to do what it will with the electron once it gets excited. And so the ionization will be strongly enhanced by the attosecond pulse train. The time of release is now ours to control because we can choose the delay. The properties can be tailored by tailoring the properties of the attosecond pulse train. So I can change the duration. By changing the central frequency of the attosecond pulse train, I can have the electron be born with an initial velocity. I can put a chirp on the electron wave packet, which is different from the intrinsic chirp that a tunneling wave packet would have. If I was doing a molecular system, I could, for instance, ionize out of several, let's call them orbitals, simultaneously, right? So this ionization step, right, you want to take the ionization step and separate it from the IR, strong field dynamics. So I think of this as taking the three-step model and breaking it open, right? Because the three-step model is very lockstep, right? Ionization followed by acceleration of the field, followed by whatever it is that happens, right? And so if you can break those first two steps apart, you gain some interesting insights, as I'll show you tonight and on Friday as well. So the idea is, could we control high harmonic generation at the single atom level? not as a way of producing more photons or killing anything, but as, could we do it and learn something? Would we see anything interesting? And the answer to all those questions is yes. So the idea is we're going to do the calculation in the experiment in helium with harmonics that are produced in argon or xenon. Pick out 4 harmonics, 13 to 19. You get an attosecond pulse train, which looks a lot like the first attosecond pulse train that was ever made. It has pulses that are about 250 attoseconds in duration, separated by 1,300 attoseconds. And by changing the delay between the IR field and the XUV, and the pulses in the XUV pulse, we can get time selection on when the electron enters the continuum. So, let me show you how it works. This is a single atom high harmonic generation spectrum made from in helium using an 810 nanometer wavelength laser pulse, 27 femtoseconds. The peak intensity is 4 times 10 to the 14. This is a calculation. It's a single atom spectrum, and the technical word for this is it's a mess, right? It's really junky and all over the place, except right out at the cutoff where it's really well resolved. And we know why the harmonics are not well resolved, right? Because we talked about the different quantum space-time trajectories and how they have different intensity dependencies, right? And so we talked about that for most of the harmonics in the plateau, there were at least 2 ways that they could be made. And the long trajectories give very broad spectra because they have a high intensity-dependent phase. And I'm so jealous, I wanted to use the blackboard. So the phase on the Qth harmonic will look like some phase coefficient times the intensity, and this intensity is a function of time. And so the frequency is going to be given by the intensity, by the time derivative of this phase. So this is going to look like alpha Q. Near the peak of this, it's kind of Gaussian, whatever it is. It'll look basically quadratic in time. Let me just expand it out around the peak since this is a nonlinear process. And so I'll have the time derivative of this, and I'll get something that looks like minus this phase coefficient and time. Here's tau squared. So I have something that looks like a frequency curve, right? The frequency is changing with time. So this is going to take my nice harmonic that might be located at exactly omega sub q, and it's going to broaden it out. And the phase coefficients are such that at intensities like this, the harmonic is broadened well beyond the spacing of the individual harmonics. And there's also, of course, the interference between all the different ways that things can be made and all that stuff. So in the strong field approximation, you've got tunnel ionization, you'd ignore the atom, you do the stationary phase approximation, you would get these paths that have these intensity-dependent phases. You'd sum over these things. The action would be proportional to some phase coefficient times the intensity. And basically, in the time-dependent driving field, the intensity-dependent, it leads to a chirp in both time and space, as we talked about yesterday. And this makes the single atom spectrum not look like a frequency cone at all. Right? And so in an actual experiment, as we talked about, the long and short, the different trajectories spatially separate, and that's why this same 27 femtosecond pulse in an experiment where they looked at the radiation on axis would look like a nice frequency cone, no problem. And if we did our full space-time calculation like I talked about yesterday, we would get on axis also a nicely resolved frequency cone. Right? So it's only at the single atom level that it looks like this. Okay, and oh, there it is. There's the chirp. So B sub I, the chirp coefficient, just like Paul was talking about, is the phase coefficient, the intensity, the peak intensity, and 1 over the duration of the pulse. So short pulses make bigger chirps than long pulses, and higher intensity. But these phase coefficients are just pretty big. So yes?
Just to clarify, so do you have to take the propagation in the medium into account to get a clean spectrum, or do you just have to count only the harmonics emitted in the propagation?
Try again.
Is there a way of doing single atom calculations so you get a nice spectrum by somehow eliminating the long trajectories?
So, right, you can do it in such a way as you can eliminate the long trajectories. For instance, you can, they are actually long, as in they go far away. So if you have like an absorbing boundary and you bring your absorbing boundary and creep in, you will start to clean up your spectrum. You'll be eating, it's not a way to calculate anything, it's a way to show yourself something, because you also eat away the short trajectory. You never know exactly what you're doing, but you can clean it up by spatially eliminating them.
The propagation in the medium cleans it up.
The propagation in the medium cleans it up already because the intensity-dependent phase, because you have a transverse intensity dependence in the focus pulse, leads to curved waveforms for the long trajectories and flat phase for the short trajectories. So you propagate and then look on axis or look off axis, and it works. But interestingly enough, when we do this thing where we run the ionization is now by the attosecond pulse train, and the IR pulse is only doing the acceleration and bring the electron back. Now we can use the seeding of the ionization to pick which space-time trajectory is populated and which is not. And so this is now, I'm going to show you a series of spectra calculated for these same conditions. The black one is always going to be that crappy one where I have just the IR pulse. All right? And now I have the IR pulse plus some harmonics that are seeding this. So you'll see like there's 4 really big harmonics here. Those are the ones that are put in. You put in harmonics 13 to 21, and those are the ones that are kind of big over here. And so now we're going to look at the single atom spectrum as a function of delay. And it's very interesting. The first thing to tell you is that when we add the attosecond pulse train, the ionization goes up by a factor of 10. All right? So the attosecond pulse train is really driving the ionization. Interestingly enough, though, there are delays that you can pick where the harmonic generation spectrum is unchanged. That's actually my favorite result out of all of these. In other words, it's possible to put 10 times as much stuff in the continuum and get no extra returns because you put it at the wrong time. Right? You put it at a time where there is no stable returning trajectory. And so if you had any doubt about all this mumbo-jumbo about space-time trajectories, that really, to me, that's actually the best proof that there's something real. But it's also the case where you can do, you can pick a delay where you get a lot of enhancement, consistent with having 10 times as much stuff, but the spectrum is still junky. And there are also, look at this, there are delays where you can do the calculation and you get a beautiful comb of well-resolved harmonics out of a single atom calculation. And that's because you launched the wave packet at the time that corresponds to populating the short trajectory. And the short trajectory, because it has a small phase coefficient, has no chirp, so it doesn't get broadened. Right? So I have a 1990s movie of this. So here is a certain delay, and I'm getting a lot of enhancement here. Let me see if I can push the button. Yeah. And as I change it, so here's my IR cycle, here's the attosecond pulse train, and again, black is always the IR only spectrum, the red is with the harmonics. The seeding harmonics are here, right? So I'm not cheating. When you look at the harmonics out here, I did not put those in, right? They got made. Okay. So as I change the delay, as I march across here, you see the single atom spectrum changes a lot. Sometimes it's enhanced but junky. Sometimes it's very nice. And sometimes there's not much at all to write home about there. That's a good one. And then it kind of comes back. So let me see if I can do this. So there are delays where there's no change. That's like if I put the attosecond pulse train over here where there are no returning trajectories, I get 10 times as much ionization, but no bigger polarization for that. No bigger transient nonlinear polarization. You can call them photons if you want. So here's enhancement, but long trajectory like, that's over here. And here is enhancement cleaned up, and that is the short trajectory. So what you get with this is your ionization driven by the attosecond pulse train. The timing selects. The timing of the attosecond pulse train selects the release time and trajectory. The short path gives a nice spectrum. The long path gives a crap spectrum. Let me look at these slides. And you can even look at, I don't know if you can see it here. Probably can't, but that harmonic is really narrow, and if you look at it, you see how they get broader and broader and broader? You can actually, the strong field approximation makes a prediction for exactly how they get broader and broader and broader, and these fall exactly on time. So here's something where I want to differ just a little bit with Margaret, and just a little bit, which is there's actually nothing special about tunneling. It's the strong field. In other words, if you look at these harmonics, if you look at their chirp characteristics, their phase characteristics, even their return time, there's nothing different than the regular strong field trajectories that would have been made by tunneling. And this is because now I use highfalutin language that I don't really understand. But I mean, there is some classical dynamics that organizes all of this, and that is there in the strong field and the continuum dynamics. And you are either able to populate one of those returning orbits, if you want to call it that way, returning trajectories, or you don't. But there's no other way to run the process. You get on that train or you don't. And so with tunneling, you sort of get on the train in a very nice natural way. With the attosecond pulse train, you sort of have to maybe hesitate a little or run after it, right? And that's why the optimal time for the attosecond pulse train to come to populate the short trajectory is not exactly at the same place as the tunneling wave packet would be, right? So there's a little shift in the birth time. And what does that little shift do? It allows the wave packet that you're making with the attosecond pulse train to catch that train that comes back. Not sure that analogy worked, but I tried. Yes?
Why can't you have tunneling with the attosecond? Can you have tunneling with the attosecond pulse?
Well,
Yeah.
so what's the question? I mean,
So you said, so when you have the attosecond pulse train, there
Right.
can still be tunneling.
yeah.
And why can't it be the same as the result of the attosecond pulse?
Because there were delay. I mean, I know what the answer is without, right? And I know if I do it at the wrong time that I get no enhancement, really no change in the signal, essentially, right? So there is still tunneling there, and it's doing what it's doing, but there's nothing extra happening. Maybe we could talk after it's still not. And you do actually get something new out of this, because tunneling is unidirectional, right? In other words, when the field depresses the potential in a certain direction, then the tunneling wave packet comes out that direction, and then it gets carried away by the field, right? But in the case where the attosecond pulse train is doing the ionization, it's making the wave packet in the center of the potential, right? And the wave packet has some initial velocity, right? Has a big spread of velocities. And basically there are two things that can happen. It can go uphill or downhill, right? If it goes downhill, great. If it goes uphill, well, it's got to turn around, and then it will be going downhill. Both of those type events at different delays lead to more or less the same spectrum. So in other words, we get both uphill trajectories that can make short or long, and we get downhill trajectories that can make short or long. And so that's kind of a new thing that